Alright, let's look at another subnetting example. It'll be another Class C network, and the scenario will be very similar. And again, before you get started on a subnet problem, again, I want you to make sure you have these questions written down and you're asking yourself this as you're trying to solve the problem. First of all, look at the network diagram. How many networks do I need? How many networks do I need? And in this case, let's say the network is again similar to the previous example. We have a router here and a switch, and we need 30 hosts on this network, and I say on this network. Now remember, each router interface defines a network or a subnetwork. We need 30 hosts on this subnetwork. And this is an Ethernet link, and this is an Ethernet link. And these are Ethernet lines from the switch to the host. Now there's 30 hosts in this network, 30 hosts in this network. And then there's a serial link to another router. You don't need to worry about this other router, but the serial link between them is also a network. So we have 1, 2, 3 networks. 3 networks. So the question you'd ask yourself is, how many networks do I need? And the answer here, of course, is 3. Now, how many bits will I borrow? Well, we also need a network address so we can determine that. So let me say again, your network address this time is 192.168, and this time let's use 2.0. And we'll use a subnet mask of 255, 255, 255.0. That means the last octet is for host bits. That means that the first 3 octets are network bits, because a 1, binary 1s, and a 255 is a group of 8 binary 1s. Binary 1s define network bits, and 0s define host bits. So the only thing we have to manipulate in our example for us to solve our problem is the last octet. The first 3 octets are fixed by the fact our subnet mask tells us they are fixed. So we're going to be able to use this octet, these 8 bits, to borrow bits so that we can perform our subnet, or we can build our subnetworks. Now, when borrowing bits, like I told you last time, we have the formula 2 to the n minus 2. And you can, like I said, you can also build a table. In other words, borrowing 1 bit will get you how many networks? Well, 2 to the 1 is 2, minus 2 is 0. So borrowing 1 bit yields 0 networks. If I borrow 2 bits, 2 squared minus 2 is 2 networks will be available. If I borrow 3 bits, 2 to the 3rd is 8 minus 2. And what is 8 minus 2? That's 6 networks available. How many do I need? I need 3. So I have to go with borrowing 3 bits. So I'm going to have to borrow these 3 bits here to perform my subnetwork design. Now the question we also need to ask is, how many bits will remain for hosts? Well, obviously 5 bits will remain for hosts. These 5 here. How many does that mean? How many hosts will I be able to support? Well, again, 2 to the 5th minus 2 is how many hosts we'll be able to support. 2 to the 5th is 32, minus 2 is 30. And again, you can build you a cheat sheet for that would follow the same as the bit borrowing cheat sheet. If you have 1 bit for hosts left, you can support 0. If you have 2 bits for hosts left, you can support 2. If you have 3 bits for hosts left, you can support 6. If you have 4 bits left, it would be 2 to the 4th, which would be 16, minus 2, which would be 14. So you can build a table as you would go across in terms of either for subnetworks or for hosts. So in this case, would this work? In this case, I could have up to 6 subnetworks. That means I'll have 3 extra because I only need 3. And it means each network could support 30 hosts. And that just fulfills the requirements we have, since we have 2 networks with 30. And 1 network, by the way, this will require 2 hosts. 1 router interface here acting as a host, and 1 interface over here acting as a host. Okay. So you'll have extra addresses on network number 1, and you'll have no extra addresses on these 2 networks, this one and this one. All right. What would the new subnet mask be if we're borrowing the first 3 bits? What would the new network mask be? Well, let me clear up some space here for us. Alright. A subnet mask comes in a form of either 128, 192, 224, 240, 248, 252, 254, or 255. If there's 1 network bit, it's a 128. If there's 2 network bits, it's 192. If there's 3 network bits, it's 224. If there's 4 network bits, there's 240, and so forth until we get to 255. Here there's 3 network bits. So because there's 3 network bits, 224 is the subnet mask for the last octet. So the overall subnet mask will now be 255, 255, 255 dot 224. I have ran out of room there. It should go there. 224. That means 3 bits. This means that 3 bits of the last octet are used for networking. That means the last 4 bits, missed a bit there, the last 4 bits here, 5 bits here, are used for host. Or that means PCs or systems that use IP addresses. Okay? Okay, let me clean up my whiteboard here. I hope you're taking good notes, and again, if you need to pause it and watch the video a little bit, that's fine. I would expect so. So we end up with this form, right? To start this problem, 192.168.2.0, and we know that this is this was the host portion we were originally given, which is 8 bits. And we know that we borrowed 3 bits to make this work. So I'll draw my dotted line here, as I often do when I'm doing these. And we'll get started here. Okay, get back to the right color pen. Alright, now the first thing we're going to do is solve for the first network address. And let's say in this case what I want from you is this. I want the first 3 network addresses. That's what we're going to solve for. First 3 network addresses. That's 1. And number 2, the first host on each network, the last host on each network, and the broadcast address. On each network. All right. Now, we start by simply using the first 3 bits, pretending they're kind of separate for a moment from the rest of them, and treat it like a 3-bit number, and the first would be 0, 0, 0, of course. Now 0, 0, 0 now 0, 0, 0 is the first network address, and we set the host bits to 0. Now, all zeros means network address for the main network we began with, so because of that, we throw this one out. In essence, we don't use it. So the first real network address is 001. And when we're determining the network address, we'll set the host bits all to 0. Let's write our number line down in case you need a little help remembering your binary number line. Okay. 001, 0, 0, 0, 0, 0. What does that equal to? Well, we know it's 192.168.2.0 or 2, right? Because that's not going to change ever in this problem. But the last octet is 32 because there's a 1 in the 32-bit position. So the network address is 192.168.2.32. And remember, the subnet mask was 255.255.255.224. Now the first host on this first network, again, the network address will be the same, and when we're determining that, the first host will be that, because if you take these bits and start counting up in binary, that is the first thing we would hit, is 00001. And that address would be 192.168.2.33. And we would very likely place that on one of the interfaces of the routers on network 1 when we're setting our IP addresses. Now the second address, and I told you I only wanted you to find the first host and last host, I'm just going to show you how we would find the second, would simply be this. And that's just simply counting up one increment in binary, going up to the next number. And that would be 192.168.2.34. 32 plus 2 is 34. That makes it look like it's a 0. Let me erase that. Back a 1. So 2 plus 32 is 34. That makes sense. That is the second host. This is the second host on the first network. And this one is the first host on the first network. Alright, now what would the last host be? Well, we would continue counting in binary. 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1 to identify more and more hosts until we got to the last host, which would be 1, 1, 1, 1, 0. Now if we put a 1 there, that would be the broadcast address. But the last host is the last address before the broadcast address. And in this case, it's 192.168.2. This one is 2.62. And if you need to take a moment to add that up, feel free to do so. Now the broadcast address of the first network is 192.168.2.63. Now it makes sense when you add those numbers up, you'll get 63 if you add this up. Now that makes sense because the next number would be what? 0, 1, 0, right? Because this position is full. We can't add any more binary digits here until we toggle over into this bit position. So the next number in sequence would simply be this. What is it? It's 192.168.2. What? Well, that's in the 64-bit position, so it's 64. Does that make sense? Certainly, because 63 is the broadcast of the first usable network. The next network, the second usable network, would start at 64. So it makes perfect sense. All right, let me clean my screen up here. The last network we stopped with was 010000000. Like we said, that one, let me skip the first 3 octets writing them down. That's going to be the same, right, every time. So .64 is our second usable network. And what I was wanting up here was the first 3 network addresses, and I mean usable network addresses. I know this is hard to read my writing, but I'll get better with this board before it's over with. Usable addresses, first 3 usable network addresses. Okay, so 010.00000 is .64. That's the second usable network address. The first host in that network is .65. 64 plus 1 is 65. That is the first host in the second usable network. You would probably place that on the Ethernet interface of the router for network 2. The second host, although I didn't tell you to find it, remember, is simply just be counting up in binary. The third host would be this, and so forth and so on. Eventually, you would get to the end, counting up in binary, until, and each one being a host address, in this case 66 and 67, counting up in binary until you got to the end, and the last host would be of this form. Remember, if it's all ones, it would be a broadcast, so the last host is of that form. And this will be, if you add them up, and you can pause it and add them up if you need to, is 94. 64 plus 16 plus 8 plus 4 plus 2 is 94. And that will be the last host on the second usable network. The broadcast address, and notice the last, also by the way, the last host on the first network was what? If you remember back, it was 62. What is the difference between the last host on the first and second networks? It's 32. And what bit are we, what's our last bit in our subnetwork split is the 32-bit. So things will increment on the 32-bit. So the last host will be 32-bit apart. The first host on each network will be 32-bit apart. The network addresses will be 32 bits apart. I mean, 32. The numbers will be 32 apart, and the broadcast address will be 32 apart. So the broadcast address here is 010 is and 11111 will be 95. And that's the broadcast address on the second usable subnetwork. Now this makes sense because if we were to, what's the next number in line? Well, these bit positions here are full, correct? 11111, that's it. To go up one more in binary, you would have to toggle the next available bit, which would be this 0. So it would be 0, 1, 1, 0, 0, 0, 0, and guess what? That's .96 because 64 and 32 is 96. That forms the third usable subnet. So 011, 0, 0, 0, 0, 0. Let me clear my board real quick. Okay, I left off there with .96 as the third usable subnet. And the first host address is 00001. This is the host range, remember? This is the network, or the subnetwork range now, actually. That is .97. That's the first host on the third usable network. It would probably go on the router interface. The following addresses would go on hosts, typically, on your network. In this case, the third network. 00010. Now that would be the second host. Again, I didn't ask you to find that, but I'm just showing you how you would do it. And you would keep counting in binary until you got to 11110. All ones with the last one being a 0 is the form we use to find the last host. And the reason being that's one less than the broadcast, which is always what? 1, 1, 1, 1, 1, right? All ones. For a given network, in this case the 011 network out here. Now if you add these numbers up in binary, you end up with 126 as the last host on the third usable subnet. The last one you could assign on the network 3 that we showed you earlier. This would be the broadcast address, which would be 127. The next number in line, that would be the broadcast address on the third usable subnet. So any network address that was between 96, so actually between 97 and 127 belongs to the third network. Now what would the fourth network be? We don't need the fourth network. We've solved the problem here. But what would it be? This is full, correct? 011. Or I mean these two bits are full. 1 and 1 here. So you're going to have to start over here. 1 0 0. And of course we'd be setting the host bits to 0 to solve the network address, and that would be, if we look right under the number line, .128. That makes sense, correct? It's just the next number in line, and that is this example. Review it, go over it if you need to again if it doesn't make sense, and keep working at it. We're going to have plenty more examples, and we'll make sure you get this.